Ladies and gentlemen, we have the interview you've all been asking for. Now, we've been covering the work of Dr. Valentina Zharkova for about 5 years on this channel. And we have a few questions for you, Valentina, later in the show. The one pressing question I have is, why did you retract the 2020 paper? But before we get
I didn't retract 2020. The editors retract paper 2019.
Yeah, the Nature paper.
Yes, my third Nature paper. I have many Nature papers.
And why did they do that?
Because they claimed in the retraction note that we suggested that maybe when I come to the plots, I will explain you. So they claim the distance between Sun and Earth does not change. While in one paragraph, when I explained the results, I suggested that the results which we obtain, variations of the baseline magnetic field, can only occur when the Sun moves either closer to the Earth or further from the Earth. So this is what, and they suddenly become very agitated, because when Sun become closer to the Earth, obviously it brings much more heating, and explain this global warming which we have, and they become very agitated, and they retracted it on the basis that the Earth follows the Sun, so the distance between Sun and Earth doesn't change. So which I basically confirmed to be wrong, because I downloaded the ephemeris of Sun and Earth distances from the official NASA and Paris Meudon Observatory sites for 2000 years, and shown on graphs in my chapter, which was published in 2021, a year later, that this distance changed exactly as I anticipated.
Well, yeah, most scientists are well aware of the phenomenon of perihelion and aphelion, and to claim that there is a constant distance of our planet from the sun seems completely insane.
Well, it is not to me to sign. I actually put the complaint to the Springer publisher, because I said, look, your basic editor written nonsense in the retraction note. I also put the complaint to the Edinburgh University, where Professor Ken Rice, who was the one who was claiming that this distance doesn't change, as I said, and he pretends to be celestial mechanic professor. So I sent to them this chapter. I said, either he doesn't know how the distances change, he doesn't calculate them correctly, or worse, maybe he knows but deliberately mislead the public that this distance doesn't change, because this is what ephemeris show, and you have to deal with him. What the vice chancellor of Edinburgh University replied to me, that he is entitled to have his opinion, despite it is absolutely wrong opinion. It is not opinion. It is his wish list, because the distances do change.
Well, back as early as the 1940s, Milutin Milankovitch and I studied the orbital perturbations that he suggested as a graduate student. I mean, we know about the obliquity of the orbit changing, the precession of the equinoxes. We know about the eccentricity of the orbit changes over 100,000 years. And so these assumptions have been around for 7 decades. And so why would someone claim that there aren't variations? Are you fighting big climate? Is it big climate coming to get you?
No, what they were not objecting the cycles, Milankovitch cycles, because their periods are 15,000, 25,000, or 41,000 years, and the biggest one, 110,000 years. So these were all the ice period and everything happened. What I was speaking about, the Holstead period, is 2,200 years.
Mm-hmm.
And they claim that this distance doesn't change. They said this in the retraction note. So it is not like they claim personally between us and no one can see it. They publish this on the website. It is still on the website. Everyone can read it. Everyone. I can see how unprofessional they are.
Wow.
And you cannot even make them. I demanded the editor to withdraw and send me official apology for making this unsubstantiated retraction. No, they didn't say. And the publisher said, oh, we do not comment on the particular action of editors. So basically they can put
Do it.
anything, but do not respond if it is correct or not. So we basically, like in medieval era, when the monks do not allow Copernicus to say that the earth rotates around the sun and not vice versa. We're in the same era.
Wow. Now, as far as credibility, we are talking about Professor Valentina Zharkova. You have literally been in academia for 45 years. Isn't that correct? I mean, you've been to multiple universities in Ukraine. Your work, the amount of published information and the science you've worked on is so broad-based. It's amazing how unprofessional they have treated you.
Yes, and I'm very surprised that they come around. Somehow this unprofessionalism is rooted in the Great Britain. In some universities, they do not teach proper math, physics, and then they stick around those people who do not teach its proper math. And they try to make you guilty that you put the proper math because you put too much knowledge. Poor kids cannot memorize this knowledge. I said, how we were in the age of these poor kids, how did we memorize? All of us, we managed to memorize it. And we survived. Look at us. We still survive and can put. So this, to say, I don't know. I was very disappointed. I have special opinion. I don't want to put it public at the moment, but I'm writing the book expressing how people they treated, and the not least the similar what they had in Hollywood. Me Too. We had this in science every time, and so this is difficult time if you independent. But what I thought, I came to Great Britain established scientist. I didn't come as a postdoc, despite I came as a senior research scientist. I thought they would respect me, what I do. It turned out, because I came from the country which collapsed, which is Ukraine. At that time, it was part Soviet Union collapsed. They thought I came from Russia. So to tell in Scotland, if they will be calling me coming from Russia, I will tell that I came to England. So I worked for 8 years in Glasgow. After 8 years, they knew there is a different country, Ukraine, not Russia, because of me. But I remember the times when I walk into the lift and I had this butterfly in my stomach, thinking what my boss invented again to crucify me. For what? You just walking in like on the minefield. This is what kind of work it was. But it turned out that this gave me a chance to investigate his work, because I was very curious why he hates me so much. Okay, I refused his advances, but he eventually found someone who didn't refuse, who should be come down. But it turned out we had very big disagreement in the theories or in the science. Then I discovered that he had error in his calculations, in his papers. And this is why they were so afraid for me to walk in there. So for 3 years, they refused me research position, and I work in the city council. And at the same 3 years, this was exactly when my biggest success came to the science, because we published paper with Sasha Kosovich from Stanford University. We published paper in Nature. We discovered sunquakes. Probably you were not born at that time. It was 27th of May, 1998. If you Google this, you would see that all 5 continents were screaming, because first time the science become the public news. We discovered that solar flares, they produce like quakes on the solar surface, and we managed to record them and report uh, to the public. So after that publicity, which was Nature, not Nature Coms, not other, it was pure Nature. This is when I returned back to academia, started working, but I still was under the pressure. They try to diminish whatever I do, whatever. And after that, I explained what is wrong with the results. So I thought they do not pay me money, so I can explain. Now everyone is accepted what is wrong, but it took me, I don't know, maybe 10 years, and it is not in solar activity. It was in high energy physics of solar flares. So definitely I
So
got
you're a big threat. I mean, they knew you were going to check their work, or you had the ability to as a mathematician, and they were scared, and you called them on it. And kudos for you, because you are relentless, and you continue to publish papers, and you continue to move forward. You do not let that bother you.
Yes, I didn't have my choice. I needed to have a job and prove that I'm working good. And I knew that I do work good. And I had PhD students, so I had support. First, my first job at Bradford University, my head of department, Dr. Baruch, was very supportive, and thanks to him, I got he supported me. I got funding from EPSRC. I got funding from European Union. And actually, my research in solar activity started from this funding from European Union. So there were not only bad people, there were also nice people around, and they helped. But always, I have this endless competition. On whatever reason, the people from Glasgow, they have this mantra: the Scottish people are the smartest one, and they somehow become very upset when someone does a discovery and the person is not Scottish. This would my main I think my main disadvantage was that I was not Scottish, and my surname is not even British, Zharkova. I can't change it. Cannot become Mark Zharkova, but I respect they had very good scientists, and your country gave to the world probably the best scientists which put the foundation of the modern physics and mathematics. Faraday, Maxwell, Kelvin, you name it. So they're very nice scientists, but obviously something went wrong at the period. So something didn't match. If they made mistakes, they should probably admit it. But they, for 40 years, they actually fooled people and pretended that everything is fine until, as I said, when they stopped paying me for 3 years. I said, if they don't pay me, I have the right to expose mistake. If I were on the payroll, I couldn't do this because I would be afraid that they will take away. I was paid by city council. I was working very good as a project manager, and people loved what I do. Actually, Scottish people were very happy that I could explain them very nicely, unlike others, because I'm professional teacher. So I love those people. They gave me, I think, the best memories from Scotland came from these guys from council, because they were very supportive. And one of my bosses said, I didn't. He said, "You're very smart. You should not be working here. You should." He didn't know that I have PhD in astrophysics. He didn't know that I published paper in Nature, but he knew that I'm smart. He tried to push me up. I said, and I was really touched how what nice people they are there. So I can't say so, but these are not which taught me to fight. I never been as fighter as I become until I came to Great Britain. I needed, actually, in the council, they have special training courses where they send you explaining how to behave, because I was born not in this country.
Yeah.
So I didn't know what are the rules here. In academia, we do not communicate much, so no much chances to learn the rules, and you live outside natural environment with your family. But when you came to the city council, I needed to communicate with Scottish people, and they needed to train me how I should communicate correctly. So I went on all the training courses. They even sent me, I got a business degree in local government management. They sent me to the university. I passed the first year. So they trained me how to negotiate, how to uh, run effective meeting, how to stop disrupting person on the meeting, and so on. They were acting to me like mothers. So
Oh,
I see, my first mother was city council who trained me live in this environment and do things properly. So this is how eventually I learned how to explain things, because it's very difficult when someone try to suppress you. Your native language is different,
yeah.
Ukrainian, right? I speak English. If someone tells me, if I'm doing public lecture, someone becomes disruptive and says, "Oh, you speaking rubbish," you that you become have adrenaline, become agitated, you start losing the words. You stop being persuasive, right? So
Yeah.
this is they train how to deal with disruptive people. I specifically went to this course because very often on these scientific meetings, I had these disruptive people who were trying to diminish me, and they explained me, and I won. Eventually this course worked because I made the guy who made me most disruptive, who made these errors, and I exposed him. So I made him to leave the meeting, not me. I finished my lecture, and after that he stopped chasing me. So this, at least openly. So this was kind of education which I obtained in Scotland.
Well, I can assure you that it has nothing to do with your nationality, because when I was in graduate school, I was a catastrophist, and I was working with the Milankovitch theory of perturbations as creating stratigraphic boundaries, because we saw similar patterns in the sedimentary rock. And as any time I went to a GSA meeting to present, I was attacked by the entire room. It's
Ah.
yeah, time and time again, because I was not speaking their narrative.
Yeah, yeah.
Yeah.
This is the thing. The tolerance is at the zero level. It's true.
Well, I brought you on the show so that our listeners could hear directly from the source what methods you've been using to determine the solar dynamics. You talk about eigenvectors as some of the math you use. I use the word machine learning, and you corrected me. So I'd like to know, because I find it fascinating when I read the abstracts or the papers, that you're actually adding the data sets, the points of interest that you're adding are not being used in current plasma physics or solar physics.
Yes.
And what you actually do is you add new data to the picture, and then you use your eigenvectors to create what is going on, the solar dynamo. And
Yes.
so that's the question. What's making the sun go wow, wow, wow every 11 years, every 22 years?
Mm-hmm.
What's driving the hail cycle? So can you break it down from when you started to where you're at now?
Okay. Let me. Maybe you can open and give me a screen so
There it
I
is.
can. So what I will speak with you. First of all, this is my website, https solargsm.com, and most of the talks and presentation will be presented here. So run the company is ZVS Research Enterprise Limited, which also results are published there. So what we done, remember I told that when I started working first as a lecturer at Bradford University, I got funding from the European Union to do automated detection of solar features. and we created solar feature catalog. So this is first time I started doing solar activity. Before, I was doing high energy particles, solar flares, and particle acceleration and transport. So I bring you to solar activity, and solar activity is defined at the moment by the number of these dark spots, which call sunspots on the solar surface. This orange is solar surface of photosphere, and sunspot close-up picture below look like this. They have dark umber, and semi-dark penumbras, and they have leading polarity, which is closer to equator, and trailing polarity. And this is what they do. They appear on the latitude plus minus 30 degrees and migrate towards the equator. And these sunspots are used as the solar activity index. So basically, at the bottom, you see average daily sunspot number area or sunspot numbers from 1870 to 2010. And you see that the cycles in 50s and 60s were very strong, very large sunspot numbers. And on the top, you see how these sunspots are formed. So at the beginning of the cycle, with the vertical line shows, the sunspot formed at the latitudes plus minus 30 degrees of north and south are called royal latitudes. And then over the cycle, 11 years, they migrate towards the equator. And all of this is a result of the action of solar dynamo. So what are the sunspots? Sunspots, when people started measuring magnetic field, so you see this sunspot S and N. If you do increase this picture, actually sunspot, these are the roots of magnetic loops embedded into the surface of the sun. So basically sunspot is the root or trunk of the magnetic loop, like shown on this picture on the right hand side. Of course, the magnetic field in sunspot is very high, 1,000 Gauss or higher, and they always appear in pairs and the same latitude, and in pair they have opposite polarity to be in the same loop. One is southern and another is northern, and so on. So as we know, during the solar activity, when activity is low, this is this active sun in soft X-ray. Even in soft X-ray, when the activity low, like in 1996, we don't see, we have only one tiny bright point over here, and nothing appears. But when you go to the maximum solar activity, 1999, 2000, you see how many active regions and bright points are here. So this is how the solar activity changes. So when you have maximum, we have many magnetic loops appearing on the solar surface, and they touch each other like wire. And like wire, they do shortcuts, explosion, and this is why we see this explosion as flares or big jets. So basically what is happening, as I said, the solar activity is governed by effect of solar dynamo. So you have during minimum on the left hand side, you have magnetic field northern polarity on the north pole, southern polarity at the south pole, and there's no any loops whatsoever, and the magnetic field is elongated along the equator over here. Then when we move slowly towards the maximum, what is happening, the magnetic field from the south start migrating through the magnetic loops to the north, and from the north to the south. So you see how many new magnetic loop appeared. So eventually some moment between around maximum, you can have that the poles could have the same polarity because the migration did not complete yet. So, but when you get to the next solar minimum, suddenly in the northern hemisphere you have southern polarity, and the southern hemisphere you have northern polarity. So the magnetic field completely changed its polarity. To demonstrate how it works, I have prepared the video, this action of solar dynamo. So this is your background magnetic field, minimum. Then the sun starts rotating, and because it rotates quicker in the equator than at the poles, it forms all those loops. And these loops are interfering with each other and form, this is the sun and the maximum of solar activity. And then slowly this loop started migrating, part of loop migrating towards the equator, part of loop migrating towards the pole, and change the magnetic polarity. Okay? So we done detection as in this European grant of solar observation. We automatically detected sunspot, active region, filaments, and in the like close up. So this yellow one, these are the sunspots. Red one is active region, and we created huge catalogs of this data. And we thought we managed to create the automated solar activity index from sunspots. But it turned out this was not possible. We tried to represent what people created. Turned out there's a lot of human intelligence which you cannot quantify in the numbers or even artificial intelligence. So again, it was very difficult to work what they require for sunspot number, for sunspot index.
Is this because there's so many different ways of counting the number of sunspots through time? Like if you get old historical data, it's not consistent with new sunspot counts?
Yes, it is that one in selection of the preferred observer and selection of his preferred definition and so on. And again, sunspot, they have tiny, if you look at this, this is the huge solar disk, and sunspot are these tiny numbers in here. So the area covered by sunspot are miserable, much smaller than area of sun. This is why the error bars brought by sunspots for any definition are very big. This is why they use this not artificial but human intelligence to somehow unify this data. But luckily by that time, it was actually David Hathaway. He built a butterfly diagram, but not from sunspot. He built from background magnetic field. So he used magnetic field, and he shown that magnetic field also splits. So at the beginning of cycle, the magnetic field start increased at the latitude 30 northern or southern, and then slowly it start migrating towards the equator. And then when you have maximum, you don't have magnetic field, and next cycle everything starts again. So you see that magnetic field is now background magnetic field migrating towards the equator, and part of the magnetic field migrating towards the pole. So as you see, this magnetic polarity of the northern pole has southern. The next cycle it become northern, and then become again southern. So it turned out that the same happens in the background magnetic field. We done the paper then with Yelena Popova and my son Sergei Zharkov. So we produced investigated correlation of the sunspot magnetic field, which shown on the top plot. No, in the bottom plot here, which was leading polarity was northern is cycle 23, and the background magnetic field where the sunspot appear with the leading polarity was opposite to the leading polarity of sunspot. So leading polarity of background field was southern, and but the exactly opposite polarity to the leading polarity of sunspots. Moreover, in that paper, we shown that the sunspot actually appear in the places in which the background field allow them to appear. And then background field modulates this sunspot motion. Either they move towards the equator or they move towards the poles. So as soon as we discovered this one, we thought, oh, maybe we better go with the background field.
So the background field is actually allowing the sunspots to form at that particular spot on the disk.
Sunspots are formed at the bottom of tachocline in the solar interior, and these magnetic loops, they are formed inside, and they travel from the solar minimum until maximum to the surface. So basically, sunspots appear, the magnetic field of the sun allows this magnetic flux tube to appear on the surface, which we see only as sunspots because we don't see the upper part, which is this connecting flux tube, right? So we see on the bottom, if you look at back at the, hold a sec.
So you're
at the start here.
So there's only certain spots the sunspots can form, and the butterfly diagram shows that the actual geometry is being controlled throughout the cycle, and the sunspots are migrating towards the equator, essentially.
Yes, basically, what this background magnetic field allows this flux tube, this one, which is on the, like here. So it appears on the surface. We see only in white light sunspots. We don't see this top one because it is very bright and temperature much higher than orange or red of the sun. So we don't see it in white light, but we see in X-ray and UV emission. So this is why we see only sunspot. But it means that they always have this flux tube appeared on the surface. And this only happens during the maxima, closer to maxima, because this flux tube managed to travel from the bottom of the tachocline to the surface. And because of the background field allowed them, they appear on the surface and then become twisted, like I shown in the previous movie, how they will be twisted during maxima. Do you understand now?
Yeah. Now, an interesting observation that I want to throw in here is that as a geologist, when the solar polar fields reverse at that flexure point is when we get the biggest 8 magnitude or greater earthquakes on Earth, right at the flexure point. It's usually slightly before or after, but it's on the solar polar field reversal.
Oh, yeah.
And you can go back 5 decades and look at all the biggest earthquakes on Earth, and they 90% fall on the solar polar field reversal.
Well, probably it is something in that, because at that time, magnetic field, we recently shown that magnetic field actually modulates occurrence of volcanic eruptions and probably of earthquake as well. So
is that some kind of telluric current that's being driven into Earth from the sun that's triggering this?
It is magnetic field which come to the Earth from the sun. So basically, I believe what we discovered, it is correlation of magnetic field, especially when magnetic field of southern polarity, it creates very large geomagnetic disturbances on the Earth, because the Earth, the southern polarity of sun interacts with the northern polarity of magnetic field of our northern pole, and it increases geomagnetic activity, and then obviously affects the crust of the Earth and causes all these volcanic and earthquake eruptions.
Fascinating. It's the sun.
Anyway, let's return back to the sun and to the magnetic field. So we established that magnetic field of the sun actually, probably what we discovered in 2008 should have the upper hand. This is what we made the conclusion, that the magnetic field defined actually the solar activity. So what we see in sunspot is actually derivative of the action of the background magnetic field. This obviously led us to the problem, how we can define magnetic field. So we detected magnetic field, we built how it behaves. It is very complicated curve, but you can't say anything from that curve. It's just a curve, which you can look at it, you can try to put artificial intelligence, but you need to have some ideas where it come from. So what we look at what people did, smart people did with the white light. When they discovered diffraction, they discovered that if you put white light on the top, this plot, on the left-hand side, this is the white light. This is your glass pyramid, the triangle with the equals sides. So if you put white light on this pyramid because of the different diffraction law for the wave light with different wavelengths, on the right-hand side, we got this result. We got red, from red to ultraviolet color. So instead of white light, you have waves of different wavelengths. And like in shown here, the rainbow. So these glass pyramid acts on the white light as separating from white light the wavelength of each electromagnetic wave. So if this glass pyramid can do it, what can separate the waves from magnetic field? Because we see the many waves and it's so difficult to interpret. So at that time, we found the principal component analysis. This is a very nice method which allows you to take data, run through that principal component, and obtain separate components. So you clean up, you move component one, component two, component three, and the total field is sum of all these components. So it's similar like this glass pyramid.
We used a technique in the 90s to look at our stratigraphic data. It was spectral analysis and Fourier analysis. And you'd take a data set and then it would run through the computer and it would give you different peaks at cycle boundaries.
Yes, we use, when we detect it now, we publish paper using Fourier, using wavelet analysis, but it doesn't help you to get the wavelengths and to get some vector dependence on the time. So Fourier is applicable only to stationary data. So this a complication. So to say spectral analysis is good, but at that time we decided to go with principal component analysis and use eigenvectors. To explain you what are eigenvectors, I take a bit of lecture note from my first year, I think, for students, math students at the university. So if you have simultaneous equation, 2x1 plus 4x2 equals 0, x1 plus 2x2 equals 0. So if you define the determinant of this equation equals 0, so obviously this solution of this equation is a single straight line, right? Here I show how I got the solution. So my expression that x1 equal minus 2x2 from each equation. And this is the equation for this straight line, right? So since x2 can be arbitrary, we can put x2 equals c, then x1 should be equal minus 2c. Therefore, the solution can be written in the form x1, x2 minus 2c and c, or c minus 2 and 1. And minus 2 and 1 gives you direction how this line is inclined to the axis x and xy. Is it clear?
Yes.
Hello?
Yes.
Yes, it means this minus 2 and 1, this thing is called eigenvector.
That's the vector right there.
This is the eigenvector. So
Yeah.
it is not, oops, I need to connect my computer. It says that it will stop acting if I don't connect it to the power.
We always
Okay,
need the power
it's
cord.
done. Yeah, it is here. It is close. So as you see, eigenvector, it gives you direction of propagation of your particular curve. And I shown you how it is obtained in the basic system of two simultaneous equations. So basically, to explain you what is eigenvectors, you find the vector which is parallel to your matrix. So if you have matrix of simultaneous equation, you try to find all the solution which are parallel to this curve which I shown before. In mathematics, it's written matrix A by vector x equal lambda by vector x. Lambda is your eigenvalues. So, and for each lambda, then you find a few lambdas, and then for each lambda, you find the eigenvectors. So this is very simple. This is a very precise method, nothing to do with artificial intelligence. So if to say you find lambda, so how you solve it mathematically in here, you need to solve this equation ax minus lambda I is singular matrix with ones in each in the main diagonal. So this is what equation a11 minus lambda, a12, a21, a22 minus lambda. This is the equation you need to solve. Oh, it's called the characteristic equation. To simplify it, this describe you, it become quadratic equation if you have two simultaneous equations. And trace A is the sum of this vector a1 plus a2, and determinant A is determinant of this matrix. So as you see, nowhere I use any assumption or anything. I just use what I see in the equations, right?
Yeah.
It's characteristic equations. So here's example. You have matrix 1, 1, 1, 4, 1, and you want to find the solution which are all parallel, find eigenvalues for all the vectors which are parallel to this matrix. So we basically substitute, introduce the characteristic equation and find lambda 1 equals 3, lambda 2 equal minus 1. Done elementary, the pupil with A level math can solve it, not a problem whatsoever. So how it is applied? So you understand now that eigenvalue describe you some directions. So you probably have few solutions. If you have a quadratic equation, we can have two eigenvectors. And what we can do, we can always, you have eigenvector 1, 2, but you can always multiply by any coefficients and you obtain the same solution. So it means that if you found eigenvector in some particular time, you can multiply by the scale of time and transfer this eigenvector time forward and backwards, and it will stay the same because this is the property of this solution. Okay? So now what we do, how we apply this, why do we need quadratic equation? Normally, second order differential equation is called the wave equation. It is used to describe waves. And strangely enough, this approach with the eigenvectors and eigenvalues applied to ordinary algebraic equation is applicable to this second order differential equation, because I can replace this equation. I can say that my x1 equal y and x2 is derivative of y. Then I can say that x1 derivative is equal x2 and x2 derivative, I do calculation in here. Therefore, I can describe that my differential equation can be written as a matrix, like written in here. So the one which the first derivative will be 0 because we don't have. This one equal 1 because we have only one equal to x2. And these are the trace determinant A C by A minus C by A, and trace minus B by A. It comes to this to the lower row. And now when we manage to replace my wave equation with the system of two linear first order differential equation, we still can find the solution using the quadratic equation a lambda squared plus b lambda plus c, and find the solution of this equation. Here's example. If you have equation, my students do it within a week. I think it was the third week solving differential equation. They do it elementary within half an hour. So this is how you convert second order differential equation into the system of two order into the system of first order differential equations, like here x1 prime, and this is its first lines corresponding to x1, and x2 prime is the second line corresponding to the second derivative, and this is your right hand side. So for x1 you don't have right hand side. For the x2, right hand side is what is in the equation on the right hand side. So this is the thing which you apply to the second order differential equation, and you define its eigenvectors and eigenvalues. So you solve characteristic equation. And normally it's beautiful to solve the second order differential equation, because if this is my equation, its characteristic equation, basically, instead of second derivative, you put lambda square. Instead of first derivative, you put lambda. C stays as C, and this is your characteristic equation. You found lambda 1, lambda 2, you found your eigenvalues. This is it.
Beautiful.
So no any manipulations. So we found eigenvalues, and my solutions are then written through eigenvalues. So the solution is constant 1 exponential lambda 1 to t plus c2 e to lambda 2 to t. And everything depends which is your lambda 1 and lambda 2. It could be real roots not equal. It could be real roots equal, or it could be roots can be complex, where we get waves. So we see that all waves are solved through the eigenvalues and eigenvectors. So this is nothing to do with artificial intelligence. This is the theory of wave formation and solution of differential equations.
Yeah.
Okay. This is the solution when your lambda is complex. So if your lambda is mu plus I complex nu, then your solution look like this. This is part which is real part, and cosine nu t plus sine nu t, which part comes from the complex number nu in here. Therefore, you got your lambda, you got your waves, right?
Yeah.
Nothing artificial intelligence, just basic mathematics. Okay? Now, we of course have waves, but we got much bigger matrix. Remember, you specifically spoke about that we got the full background magnetic fields from the North Pole to the South Pole. It's about 1024 pixel by 1024 pixels. So we have much more data than 2 by 2. So we need to do something with that.
Well, and the data set, when does the data set begin? In like 1920?
Our data set beginning of 1976.
Okay.
Wilcox Solar Observatory.
All right.
Prepared by in Stanford University. It was PhD work by Todd Hoexema, who is a great friend of mine, and been working with him and his colleagues. So they created this brilliant telescope, and they created the measurements which carried now the fifth solar cycle. This is a huge advantage because the measurements are very clean and uninterrupted.
Well,
Very small interruptions.
now that everyone's head hurts because we did graduate level differential equations on the show, what did you find out after you determined the math and you crunched the numbers? What is it that was revealed?
Yeah. First, to say you that if you have complex numbers and have here with specific numbers when we don't have a real solution, only wave solution. This is my solution I've shown here. This is the wave equation. So this sine cosine function, this is what we obtain. How we work with principal component analysis, it's not brand new methodology. It's done by Pearson 1901. It's 122 years old methodology. So basically what you need to do, you want to convert correlated variables x1, x2, xp into something which are new variable which are not correlated. At the moment, all magnetic waves are got together, and what I measure as a magnetic field from each pixel, it involves all waves which already added into it. So this what we call correlated variables. So what we needed to separate them. We needed to find some parameter delta here, delta t, delta 1, delta 2, which allow separate them into separate entities. But this delta should be normalized because when you put them into square, they should be equal to 1. So this is kind of approach which we can use. And then we try to find the data with maximal variance, and we calculate covariance matrix of these variables. Basically, we solve the similar problem with the covariance matrix on the eigenvalues like we solve for these linear equations. Do you see? The equation nearly the same, yeah? It was, in my case, was ax minus lambda ix. Here we remove x, we left only covariance matrix, left this lambda matrix, which define my eigenvalues. But what we do now, we use find the coefficients, these coefficients lambda, they are separated by variance of the data. So we evaluate the data variance in an order these eigenvalues from highest value of the eigenvalue to the lowest. So basically what we do, if you do this, we obtain so-called scree plot. We obtain, so this is my eigenvalues. On the left-hand side, this percent of variance. So the highest eigenvalues are these ones, which one is contributing 20% of variance and another is about 18% of variance. But you see, they come very close together in pairs. And then you have the next set of double eigenvalues with the variance about 9% each, altogether 18. This is the second one. So this is what, after we've done this operation on separating eigenvalues for, we used 15 plus 15, 30 latitude strips for which we average variation of magnetic field on the longitude. So we managed to find these eigenvalues and managed to calculate the variance. And we found for each eigenvalue, we found variance which is responsible for the data contributing to these eigenvalues. And we found that the first pair of eigenvectors, they correspond to the data with variance altogether 38%. The second pair, 18%. The third pair and the fourth pair, altogether, they contribute about 95% of the variance of the data. You can add further, but we only use the first 4 pairs. But in the first paper, 2012, we only use the first pair. We obtain the scree plot. These are eigenvalues. And then we needed to produce eigenvectors corresponding to these eigenvalues. And this is what we've done. So these are eigenvectors corresponding, the blue one corresponding the 120% of variance, and the red one to the 18% of variance. So we discovered that in the magnetic field of the sun, background magnetic field, there are 2 waves, not one wave. What each dynamo model, most of them work that dynamo produces a single wave and then it changes every 11 years. They couldn't actually obtain the period 11 years. They obtained first 8 years, then they started taking some different disturbances to expand this period and so on. But what we found, this was the first time, we found that there are 2 waves. So obviously the dynamo works, not a single dynamo, it should be double dynamo. This is what we discovered. And we discovered that this double dynamo should work in different layers. And what we observe as a resulting curve, this is what we observe, a summary curve. This is the summary of these 2 curves. This is what we obtained in paper 2012. In paper 2015, we managed to actually describe now these 2 curves. Remember that because we separated from the whole set of waves, we now cleaned up and separated 2 waves, which we think are produced by dipole magnetic poles. So on the northern and southern polarity, these are 2 waves produced by dipole magnetic field. And because they are produced by dipole magnetic field, it turned out that we can quantify these curves with analytical expressions because they now are clean from any other contributions done from different other waves. Remember, their lower variance, they put a lot of noise into it. We remove all this noise. This is the clean data. As soon as we clean data, we managed to find mathematical law for the first component and from the second component. And what is remarkable in that it is not simple sine and cosine. It is a product of sine and cosine with the amplitude A. And the period of phase between the wave also changing like cosine. None of the dynamo models predict this behavior. It explains why they cannot predict with dynamo model the solar activity beyond one single solar cycle, because they do not include some probably processes to obtain this solution. So the at the moment model is not fully functional to represent what we derive from magnetic field. But we add these waves, and we thought 2015 and 14, we said, what did we get? Oh, we see that amplitude of this wave decreasing. Yeah, you see cycle 21 amplitude 600, 400, 400, no, 600, 600, then 350 in cycle 23. In cycle 25, it will be amplitude up to 200. But in cycle 26, amplitude drops below 100. So, what we get? Let's compare this with the sunspot numbers. So what we did, as you see, we negative magnetic field, southern magnetic polarity, we assign it as negative magnetic field, and northern polarity is positive. So we thought, why don't we reflect everything into the positive polarity, right? In the positive semiplane. So when we reflect it into the positive, which is shown by the black curve, this is our modulus summary curve. And the red is sunspot numbers, which obtained from the known catalogs. So what we discovered that this our modulus curve actually describe the sunspot numbers. They're not fully fit, but they more or less follow the description of it, right? So when we discovered this one, we managed to predict, again, remember we have the formula describing these two curves. So we can calculate, we were in cycle 23, we could calculate the cycle 24, a cycle 25, a cycle 26. So this is how sunspot should be acting. And what we discovered, that in cycle 26, the solar activity will drop very dramatically. And it dropped very dramatically. We done recently paper monthly notice, we added cycle 24, but my eigenvalues, the eigenvectors stayed the same because they derived precisely, so they do not change. This disarms all the critics because they simply do not understand what are the eigenvalues. I explained specifically here that eigenvalues and eigenvectors, these are the precise solutions. They're not artificial intelligence. We don't do any assumption. We derive everything from the data. Okay?
And all this data is coming specifically from observations of the sun and sunspot.
Exactly.
Yeah.
Exactly. So this is observational data. Everything so far, we didn't include any theory whatsoever. It comes from magnetic field of the sun.
So also you're showing on there cycle 27 appears to be just as weak as 26 as well, based on the summary.
Yes, it is. We can come further because now we have the formula. We calculated this formula for 2,000 years from 1200 to 3200 in here. And voila, this is what we discovered, that basically this is my, in oval, I shown the cycles we used, cycle 21, 22, 23. This is cycle 25, this is cycle 26, this is cycle 27. And from cycle 28, the solar activity starts growing again and comes back to normal. And it turned out that actually the amplitude of solar cycles changes every 350, sometimes 330, sometimes 380, but in average 350 years. So these two waves, they interfere with each other and causing this kind of beating effect. So they modulate the amplitude because they have phase difference. So they have frequencies which are close but not equal. And this causes modulation of the amplitude. So to explain you, I can probably bring you here, wave interference. So if you have two waves on the top, you see one wave runs away from another. So they have phase difference. When the waves have the same phase, the amplitude increases. Look, waves got the same phase, amplitude increased. When the wave become into antiphase, amplitude becomes 0. So if you have two waves, y1, y2, when you get together, they have either constructive interference, the amplitude increased by factor 2, or destructive interference, the amplitude becomes 0. So this is exactly what we do again from from the equation, wave equation, and we assume that we have external force induced F cosine omega, and the system has its own oscillation omega 0. So if you solve this equation, you obtain this kind of solution, but the solution will be difference of cosine omega t minus cosine omega 0 t. And we assume omega and omega 0 are close but not equal. So now we apply formula for difference of cosine function, which written in here in green. And voila, what we got. My amplitude varies. This is the factor which you obtain from there, but this is the function which modulate the amplitude, which equal difference between two frequencies divided by 2. And this is the frequency of this one, envelope wave. And this is your waves from which you started. Now they oscillate on the frequency omega 0 plus omega by 2. And this is my oscillation of the solar cycle. This is exactly what we observe on the sun. This is called a beating effect. And beating effect, each of you who have piano at home or tuned violin or whatever, they know that the engineer comes with the fork, hit the string, and listen, if there's the beats, then he knows that he needs to increase the tension or decrease the tension to remove the beats. So this is beating effect in the sound. But on the sun, we don't have engineer, so we have no choice. We have to deal with this beating effect. Voila. Okay? Hello?
So if we could tune the sun, it would no longer ebb and flow. It would just be constant.
Yeah, but we can't. Luckily, we can't.
Yeah.
So far, until probably we find so uneducated people who will try to disrupt the sun, but at the moment we can't.
It appears as if the canceling energy that is coming up the next few decades appears to be more severe than the Maunder or the Dalton minimum.
No, it will be similar like Maunder minimum.
Okay.
Only it lasts only 3 cycles, while Maunder minimum
Yeah.
lasted for 6 cycles. So it will be shorter than Maunder minimum.
Okay, beautiful. That's
Yeah,
good
so-
news.
Yeah, this is what we obtained from observations. And on the top, we applied the model. If we come back, I jump through the model. So we use the model. Remember that we discovered there should be 2 waves. One wave is formed at the bottom and close to the convective, on bottom of the convective zone. And the other layer is close to the solar surface. So we solve Dynamo equations, 2 Dynamo equations for both component. It is for poloidal field and toroidal, which is in sunspots. And what we need different, we assume that it is a different speed of meridional circulation in these 2 layers. So you see one layer shown by blue and another layer shown by red. And they have difference in this velocity. They come move in the same direction, but difference in the velocity has to be maximum 1 meter per second. Difference produces this beating with the period about 350 years. And these are, with the 2 layers, people managed to report the similar. We assumed that should be 2 layers. There were theory developed with the 2 layers, but no one observed 2 layers. We confirm it from the observation of magnetic field that should be 2 layers. And this guy, Zhao et al., they actually derived from helioseismic observations with the HMI on SDO satellites. They discovered it should be also 2 layers. So we independently came up to the same conclusion, which is very unusual, but terrific that the guys managed to do it. So this is what we got beating effect. Now we can reproduce with our model, Dynamo model, the waves in the past 2000 years. So at the bottom is our observational curve, which we derived from the eigenvectors and their interference. And this is what we managed to reproduce by feeding the dynamo parameters to fit this curve. And you see they're more or less resembling each other. So it was Elena Popova. She's our dynamo person. She works now in Chile. She managed to do this simulation, and we impressed. This is the first time when Dynamo could produce the waves for 2000 years. Normally they produce maximum one cycle ahead. So this was interesting. And this result was reported in the paper 2015.
Wow. And this really makes people angry.
Yeah, this is why so many people say so many bad words about us, because they suddenly become very upset. Why would they come? And these bloody two women, me and Elena, and two men, Simon and Sergey. So I don't know. We happily we're happy to share, but we're happy to share people with people who are positive, who are interested to look and find if you have any question, because we had improvement of this model obviously since 2015, but when they done, we have some discrepancy, and like Usoskin started writing different nasty comments under this paper. Luckily the editor at that time was smarter, so we needed to place a reply to Usoskin comments and publish in 2018 into Journal of Atmospheric and Solar Terrestrial Physics. So we published, we managed to answer the question and dismantle the accusations. So this is was sorted, but it doesn't come down those people, because it turned out they were putting forward idea that the sun doesn't have this, stable heartbeat. They said the sun has stochastic dynamo. So it is like a person who has with tachycardia. I said, if sun would have stochastic dynamo, it would explode within next, few years. It's impossible.
So that's funny. But how does the summary curve that you've honed in on for years, how does it correlate to the known proxy data going back 800 years with like the Oort minimum? And did you nail all that? Is it all in the curve? Do you have an overlay?
Yes.
Okay.
Yeah, first of all, here is we calculate for Mount Grand solar minimum, we calculated the butterfly diagram. And when you see this max on 1720, so my butterfly for that correspond. This is for 1700. So we managed to reproduce sunspot in Mount the minimum. Then we now paper is under the review, but we managed to compare our curve with that one from sunspot number, and discovered that whatever they done in sunspot number until 1900, it was a huge mess. They simply shifted max and min. I don't know how have they done it. Yeah, so, and we discovered by that time when they shifted, there were no basic observations. Sometimes there were 20, 50 observations per year. So whatever is written there, some cycles were duration of 7 years, some cycle duration of 8 years, some cycle 15. So definitely they didn't pay attention at that time. It is actually beginning of 18th century. And on top of that, at that time, the whole world came from Julian calendar to Gregorian. So
Right.
in the 18th century, somewhere in the middle, most of the Europe started going to Gregorian, but they came all in different times. But when people do the drawings, remember at that time telescopes were not present, so they did drawings. When they do drawing, they put local time, which they know it is, but never said whether it was Gregorian or Julian. So this is why the correspondence from 1900, when the data more or less between our curve, which is green line, and sunspot curve, more or less, apart from the amplitudes, but they are different amplitudes should be, because the sunspot represent toroidal field and green is the poloidal field. So the amplitude should be different. We tried, this is the curve for sunspot. So it is all in our hands, and we know how to work with artificial intelligence and publish a number of papers. So we decided to actually fit our curve to the sunspot cycles. This is how we discovered that it is not possible. Something wrong with the cycles, how they defined before 1900. Because when you feed this one, suddenly, if you put these parameters into the curve, into the eigenvector, suddenly all the grand solar minimum disappear. So that they become like straight line,
Hmm.
or amplitude of the cycle becomes similar, which complete nonsense. So in this is how magnetic field, this is the poloidal magnetic field, which we measure from, and this is half toroidal, which measured from sunspot. So this is background field. So you see the amplitude are different. The amplitude could be probably close in the middle of the cycle, but they're quite different amplitudes in the uh, both wings of the cycle. So if the amplitude different, not a big deal. But when we calculated the wavelet analysis, so this is for sunspot number, the average period 10.7 years, and this is the modulus summary curve analysis from our curve from 2015, we got the same period, 10.7. So obviously it works fine. Also, we got this period 342 years for this particular 2000 years, which is grand solar cycle. This is the one. Red curve is the red noise, which is we generated to show. So everything which is above red noise is these are real peaks. So this is real peak, and 342 real peaks. All other peaks are the level of the background. So this
So
is spectral analysis.
the grand solar minimum cycle that you're determining here is 342 on average.
Uh, yeah, for this 342 or 350, yeah, kind of.
So what do we refer to low periods of solar activity in between there that aren't the actual grand minima, like the Dalton minimum?
Yeah, the delta minima, they belong to the Gleisby cycle, which is about from 80 to 100 years. This is a different cycle, which is introduced by the second set of magnetic waves. Remember which ones in the scree plot they had 18% of variance?
18, yeah.
Yeah, this is quadruple waves. If we add quadruple waves, we get Dalton minima. So
And
they
centennial
introduce,
minimum,
yeah.
because
So
that's 100 years later.
yeah, they do every 100 years, 90 years. So in this model, we didn't consider yet this quadruple. We done this in the paper we published 2022, 2018 with Elena Popova, but we didn't include yet into the full cycle. So we, at the moment, we work with the polar dipole magnetic field. And this is why the Dynamo model fits so well, because they all develop for actually dipole magnetic field. When you add quadruple, we got extra cycles, extra minima, Dalton minima. But in this approximation, they are not yet present. Okay.
Yeah, excellent.
Well, so here are this, just to prove you, this is the paper which is now under review. Hopefully, will be published shortly. So if you take the full data, we compare. The green is our um, cycle produced from eigen vectors of background magnetic field, and red is sunspot. So if you put the whole data from 1700 to 2020, the correlation between them 25% very low. But we know that they have problems with the data migration. So we knew that Muslim migration finished 1860. So if you took 1860, the correlation become 56%. But if we start from 1900, where all people who restore solar cycle agree and the solar cycles are more or less correspondent, the correlation becomes 67%. And this is exactly if my data, remember the variance is 38%, which means that if you sort this data by standard deviation, it gives you 67% exactly. So this is the maximum we can get from the data for dipole magnetic field, and they correspond very nicely to sunspot data. So this is what we discovered. So hopefully it will be proof soon. And now we come back to.
So does that mean that there's a 67% chance that we are in grand minimum?
No. This is correspondence of our cycles produced by magnetic field, background magnetic field of the cell, corresponding to the cycle produced by sunspots. So these are not defining what we will be, but we will be in grand solar minimum anyway. We already entered it because we predicted in paper 20, where we are now. We are here.
So would you consider the beginning of cycle 24 as the beginning of this grand minima?
No, grand minimum started 2020 from the minimum between cycle 24 and 25.
Okay.
So cycle 25 is the first cycle of the grand solar minimum. It will be cycle 25, 26, and 27. So from 2020 to 2053.
That will, in fact, be one of the shortest grand minimas because they usually average 40 to 70 years.
Yes, it will be. Yeah, it's correct. And this brings us back why they considered previously eddy, for example, they seen that variation, the solar radiance deposited to the Earth was following the solar activity numbers, sunspot numbers. So this is what the sunspot number increased and solar radiation increased. When Maunder minimum came, solar radiation dropped very dramatically by actually 3 watt per square meter in here, and the temperature was slightly decreased. So this would basically would happen. But here is what Lean et al. 1995, they did investigation and found that decrease of the solar radiance during Maunder minimum was about 3 watt per square meters. And here on the right-hand side, the temperature variation during Maunder minimum. So you see the temperature reduced by about 1 degree. And every time there's a Dalton minimum, another Dalton, it decreased half degree. But during Maunder minimum, it decreased by about 1 degree. And this is what we would expect in the current modern grand solar minimum. The temperature would decrease up to 1 degree. And the guy Schindel et al., actually in 2001 in Science, they investigated how the surface temperature on Earth was reduced over the globe during Maunder minimum. In Europe, mostly in Northern America, they went into the deep freeze. They had glaciers extended, sea ice scraped south, and rivers are frozen. So possibly we will have similar picture. I don't know. You can read this paper. If you type Schindel, they still have the science you need to be subscribed, but they have explanation on the website which they haven't removed, and these plots are available. So you can look what happened in the southern hemisphere, obviously. But as you see, the temperature up to 1 degree was in the Northern Hemisphere and Northern America and Canada, exactly where we had these jets before Christmas in America. So obviously there is something very similar happening now. And why it is happening, what this guy said, a drop of the temperature was related to drop abundance of ozone created by solar ultraviolet light in the stratosphere. And because of that, less ozone affected planetary atmospheric wave. So when the ozone is stable, the planetary waves, stable jet streams, follow this straight line. When less ozone, it causes wavy veins, atmospheric waves, then in turn cause the giant wiggles in the jet streams, and shown in this picture. And it kicks the North Atlantic Oscillation, which we observed. Probably we start observing this, what we had before Christmas in the UK, before Christmas and over Christmas in the United States and Canada. And now we have in Siberia, they have frost, the coolest weather they ever recorded, minus 60 or 65 degrees Celsius. It's horrible. But this is what is happening, cold air coming back because ozone, and this is on the beginning of the grand solar minimum. We have another 30 years ahead of us. So the worst will come probably from 2035 to 2045 when we will be in the cycle 26. This will be
Yeah,
unusual.
and some of these side effects are they're all related to the sun's weakening magnetic field. As the sun is
weakening magnetic field and UV radiation, which important for ozone layer in the Earth's atmosphere.
Yeah, because we talk on our channel how the ozone hole or ozone depletion occurs at solar minimums because of more cosmic radiation coming into the Earth. And when you get a solar max, the ozone hole heals itself because there's less things affecting the ozone. We're also going to get an increase in UVB, right? Yeah. So this may affect plant growth as well over the next few decades.
Oh yeah, but the government actually need to forget about global warming for time being and think for the next decade or two about this mini ice age, because we need to bring greenhouses on the earth and grow vegetables and fruit there because we will not have them. It will be snowing, will be cold here.
Yeah. That's one of the reasons we're out here is we've been building geothermal greenhouses. We've been teaching people how to be self-sufficient for the times that are coming.
Absolutely. It is absolutely correct. Well done. But the government should be thinking about this.
We got to get on the government. They always love us. They love us so much.
We know this.
Well, Valentina, this has been an amazing conversation. We're going a little long. I wanted to talk about the sun's connection with earthquakes, and maybe we could do that. Let's do that in a future podcast. Would that be all right with you?
Let's do the future podcast. I live on this snow blizzard in US and Canada and grand solar minimum. There more to come. They now wrote in newspapers, there will be end of January, there will be another jet in the United States. So if the people telling you there is no winter anymore, show them these pictures.
Right. The facts are we've been following the total snow mass in the Northern Hemisphere for about a decade. And in the last 4 years, it's been in record territory the entire winter. The Northern Hemisphere has record snow mass for the last 3 years. So.
Oh, really? I didn't know that.
And it's at the same spot today. It is above the 40-year baseline and in record territory. And this is even with Europe claiming they had no snow. Europe is about to get blasted with snow. You're in the UK. You just said it's minus 3°C there, and you got snow out your door, right?
Yeah, we have snow. Much more snow in the south and much more snow in Scotland. In Scotland, actually, we had an avalanche. And skiing season is flourishing in Scotland.
Do you get a lot of avalanches in Scotland?
No, only this year. We didn't have before.
Oh, wow. All right. Well, it's been a pleasure. Thank you for coming on the show and explaining your model and the work you're doing. And let's reschedule and we'll talk less, let's do less differential equations and more intellectual science.
Absolutely. But what I wanted to show you, and you have now is on record, that
Yeah.
eigenvectors and eigenvalues is a precise method, nothing to do with artificial intelligence. It is pure derived from observation, defined only by variance of the data, nothing else.
Yeah, and this is the actual data observed on the sun with the background magnetic field.
Exactly.
Yeah, so
Okay.
it's brilliant work. And now everyone that used to be confused has been brought up to speed. It's been a pleasure. Thank you for coming on the
Okay.
show.
Cheers.
Cheers.
Bye.